improved anonymous broadcast encryptions, tight security and shorter ciphertext. The talk will be given by Jingtao Li.
Okay, thanks for the introduction. My topic is improved anonymous broadcast encryption, tight security and short ciphertext. My name is Jingtao Li. This is the joint work with Junjing Wu. So let's start with the definition of broadcast encryption. Suppose we have a universe, we denote them by integers from 1 to n. If we have a message, we want to deliver it to some of the users in this universe. We can use the encryption algorithm, takes the message and the set as the input and output a ciphertext. If you are a user in this universe, you can try to decrypt the ciphertext with your secret key. And if you belong to the set S, you can decrypt it. If you do not belong to it, you cannot get the message. So that's the definition of broadcast encryption. It has a lot of application scenarios. For example, the pay TV system. Yeah, the security of the broadcast encryption requires that we hope the ciphertext has protects the message well to the users outside the set S. Even if they collude with each other, they cannot get the information about the message. Formally, we have this definition, this form for any adversary. If they can get the secret key of users outside the site S, they cannot distinguish two ciphertexts of message M0 and M1. So in this work, we want to do something more. We want anonymous, which means that we hope the ciphertext not only protect the message, but also protect the receiver site S. So formally, we have this. If you can distinguish M0 or M1, you can distinguish the two ciphertexts. If you can distinguish S0 and S1, you can also distinguish the two ciphertexts. We hope that the adversary cannot distinguish the two ciphertexts. That's the definition. A problem here is if we take the this one. Yeah, take the S as the input of the decryption algorithm. Everyone will know the receiver set, so it will definitely not be anonymous. So we hope that the S cannot be the input of the decryption algorithm. So this is the definition of anonymous broadcast encryption. That's the reason why we name it anonymous broadcast encryption rather than broadcast encryption with anonymity. So let's look at something more about the definition about the security model. So we hope to achieve anonymity. A problem here is which part of the secret key we can give it to the adversary. We now have two sets S0 and S1. It should be S0, S1 and S2. It should be S0 and S1. So for this part, this white part, we can give. Of course, we should give this the secret key of this part to the adversary. But for the red part, is more difficult. It's more complex. If we give the secret key of the user to the adversary, they can use the secret key to decrypt the ciphertext, so they can distinguish the two ciphertexts. They can distinguish from the messages M0 or M1. So we have two ways to overcome this simple attack. The first one is we do not give the ciphertext in this part, in this red part, to the adversary. So this is called a weak anonymity. In this work, we consider a more complex version of anonymity. If we can give this part of secret key to the adversary, but in this case, we require the M0 equal to M1, which means that in this case, we can only distinguish the ciphertext from S0 and S1. We cannot distinguish from the message anymore. That's anonymity we consider in the paper is this security model is first proposed by Leuven and Quaglian in 2012. This is the security model we use in this paper. So we in this work we also want to achieve CCU security, which means that the adversary except the secret key, we also allow the adversary to get the plaintext of our ciphertext chosen by the adversary. That's the standard definition of CCU security. Is similar to the public key encryption setting. Yeah. So in following, let's talk about data security. To prove that a scheme is secure, we need to show that if a problem, this statement, if a problem is hard, then the scheme is secure. So we need to prove that for any adversary, if they can break the security of a scheme, for example, anonymous broadcast encryption scheme with a success probability absolute, we can construct another algorithm B, which can break a hard problem with probability epsilon over L. L here is called a reduction loss. We hope to get a smaller reduction loss. The test security means that we want less reduction loss. This is not only a good theory result, but also give us a very high efficiency schemes. Suppose if we have a large reduction loss here, we need a larger security parameter to fulfill this gap, fulfill this reduction loss. So let's look at the state of the art. The first work of anonymous broadcast encryption is given by Bass, Boney, and Waters in Financial Crypto 2006, but they only consider passive attacks. Later in 2012, LPQ give CC security and for anonymity version, and they give a generic construction. So that's the security we consider in this paper. The other one is given by Faisal Pereira. They give only weak anonymity. I have talked about it in the security model. So this LPQ is the only paper that achieves this security requirement. So let's look at the result. In their work, they give two versions of broadcast encryption, fast version and the linear decryption version. So why we have these two versions? So let's suppose that in the ciphertext we have lots of components, lots of group elements. The decryption algorithm take a secret key as the input and try to decrypt the ciphertext. They don't know which part is useful, so they will try one by one. So they have a linear decryption cost. So to achieve faster decryption, they need to add something more here. Maybe it's 2 times the L is the size of the receiver set. So they need to add something here to tell the decryption algorithm which part is useful, which part you can get the message from which part. So that's the faster decryption version. So the motivation of this work is that we can notice that the reduction loss is not that they have a uncube reduction loss here. So we want to know if data security is possible here. The second motivation is that we already have a lower bound of this kind of anonymous broadcast encryption scheme, says that the ciphertext size should be linear with the size of receivers, but the shortest ciphertext here is 2 times L. Can we achieve only L plus something? Yeah, that's what we did in this work. Yes, we did it. We get a constant reduction loss, and we reduce the ciphertext size of both schemes. So our technique here is we use a creamer soup public key encryption scheme into the RPQ generic construction. We find something interesting, and we give some concrete optimizations and get our result. So let's start to look at review the creamer soup public key encryption. It's a scheme working in prime order group G. It's DDH hard DDH hard group. P is the generator. Okay, in the following we will use these notations because we have a more general result, but we only give a very simple setting. That is, we have two elements here. We use white box to denote elements in ZP. We use blue box to denote elements in group G. So this multiplication of the two vectors here is a simple element in group G. Is G to the key. We assume here is the key 1, key 2. Here is the A1, A2, G to the A1, G to the A2. Okay, here we have a G to the key 1, A1 plus the key 2, A2. Okay, it's clear here? It's not the very traditional notation. So let's look at the creamer soup construction, creamer soup public key encryption. So the secret key consists of 3 parts: key, X, and Y. So the public key consists of two group elements here, and key times A here, vector X times vector A here, vector Y times vector A here. So in the subtext, we choose the element from ZP at random, name R. We compute A times R, which means G to the A1 R, G to the A2 R. So this is the first part. The second part is we use this component to times the R to hide the message M. Okay, the last part we use the following two components, combine them together by alpha is a hash of the first two parts of the subtext, and this part is for CCU security. This part is to hide the message. We just need to know this. So how can we get the anonymous broadcasting encryption from CSPKE? So we just make lots of copies of CSPKE. So we have for each user we have a secret key for them. It's the same with the CSPKE. The public key, we share the vector A here by all the users in the universe. We give public key of them and just make multiple copies. Here we also use a one-time signature. Here we need to bond the whole subtext together, use a one-time signature. So the subtext is also the same. We share the randomness R here, and the following two parts we use we just give multiple copies of the subtext. So that's very trivial construction, it looks like, but in this subtext, if we want to decrypt it, we need to check which part is in the decryption algorithm. They need to check which part is useful for the current secret key. Yeah, the decryption algorithm get a secret key. They want to decrypt the subtext. They need to know which part is useful for him, right? So this is to decrypt the subtext. We need a linear decryption cost. So what's interesting here is we found we also use sigma is just a secret key to achieve CCU security here. An interesting part here is we found this part is very interesting. Is first we mentioned above here is for CCU security, right? But we found that we can use it as a fast decryption hint, we can use this part to distinguish which part is useful for the current secret key. So we just need to give a secret key. We just need to compute this part to check if this part, if there is a component in the subject is equal. Then if we found this part, we can find the this part related to these two parts can be put together. We will find this part is useful. We will decrypt this part. This we will get a faster decryption of anonymous block assumption, which means that this part is not only for CCU security but also for faster decryption. That's why we get a shorter ciphertext here. So this is our first anonymous broadcast encryption scheme. So now let's look at its security. We want to here is the scheme. We want to prove that it's secure. We need to argue that the ciphertext protects the message M and the identities of receivers well. So what we do is similar to the proof of CSPKE. We just change this part to a uniform random elements in group G2. In group G. So then we will. This is DDH assumption allows us to do this change. So after that, we will find that this element has a message M well. So I do not want to say more about the security proof, but I want to give an intuition about why we can achieve tight security. That's because we can, in commercial PKE, we can deal with all the ciphertexts in the whole universe together. So that we don't need to guess which user is in this set S. So that avoid the reduction loss. So in the RPQ construction, they use black box reduction. So they need to guess which user is in this set S, because S is chosen by the adversary. So we need to guess it. So that's why we achieve tight security. So now let's consider problem. So if we can compress the ciphertext again, because the previous scheme is suppose fast secure. If we do not need fast secure, can we compress the ciphertext again? So let's look at the ciphertext. We found only this part is useful. It's because message is only here. This is for CCU security. If we can make it, we can share this part by all users. We can achieve shorter ciphertext. Which means that can we press the ciphertext again? If we can, the answer is we can make this part publicly verifiable, so we can achieve shorter ciphertext. The answer is yes. We can use the technique back user, and we at Eurocrypto 2015. So let's see how can we do it. So first let's see the public key. In the public key, we have these three parts. To use the queues, we need a bilinear group. We need to we need to replace the previous group with the bilinear group, and then we change this part because we want to make this part publicly shared. So we do not want this part for everyone. We hope all the users in the universe to share this part. We just change this part to like this. We change the xi to only one vector, one matrix x. Is you can think it's a copy of 2 of xi here, and commit it in the. This is in group 1, in G1. Okay, y is the same. Then we put we put x and we also commit some entropy of x and y into the second group G2. B here is random element in G2. So is that clear? Okay. Okay. After that, we can make a ciphertext here like this. This part is shared by all users in the universe. All users in the set S for all the receivers. So we now put this part into the tag alpha. This is for CCU security. Okay, we found something interesting here. Is this tag has something like it looks like something. It can be used as a one-time signature, so we can remove the one-time signature. It can replace this one-time signature. It's both for CCU security and we can remove and for the how to say one-time signature. The function it can displace the function of one-time signature, so we can remove it. But we have a problem here is we do not know if we can decrypt correctly. This because we do not have this tag for everyone, so this may result a wrong ciphertext, result a wrong message. So we just replace with it a key and use the key binding symmetric encryption to avoid it. So that's our second construction. So in this paper, we just give two anonymous broadcasting encryption scheme that achieve shorter ciphertext and data security. So the open problem is if we can achieve a short ciphertext, which means is close to the lower bound is L plus something without a bilinear pairing. Yeah. Okay. Thanks for attention. Thank you.
Questions?
So, can you please give us some intuition about why you can remove the one-time signature?
Because here we have this tag. It is interactive zero-knowledge proof.
Okay.
Yeah, it has a property named one-time simulation sound. Yeah, it's similar to the property of one-time signature. Okay.
Any other question? Okay, let's thank the speaker again. The second talk of this session is time-based direct revocable ciphertext policy attribute-based encryption with short recognition list. The talk will be presented by Kai Liang.
Morning. This is my talk. It's a time-based direct revocable CPABE with short revocation. So our general scenario, the setting is in the ABE. So the ABE as a general extension of identity-based encryption. So it is it can provide some more fine-grained and expressive in data sharing. For example, you can use policy, and you can do attribute sets, and maybe some of you already know that ABE has two research lines. One is for the CPABE, and the other is for the KBABE. And the cybersec policies, attribute-based encryption, and key policy-based attribute-based encryption. And then the applications for the ABE could be cloud computing and electronic health record sharing and cloud-based storage system, and etc. And this paper deals with the CPABE. And when we're talking about the attribute-based encryption, no matter you are KPABE or CPABE, we need to consider something like revocation. And for example, I give you an identity card, and that identity card is just for your ID. And then if we regard an ABE as IB as a special case of the ABE, once your identity is changed, for example, you are currently a chemistry or computer science student, and after that you move to another for example, you're studying in Leuven as a PhD, and then affiliate with computer science department, and after that you join site, you become a double E. The start of double E, and then you actually change. And then another thing related to this type of revocation is the user revocation. For example, your company has 100 staff, 100 officials there, and then after that, maybe economics linking, and then you have to fire some of other of the workers or employees, and so that you have to revoke their key so that they cannot come back to the company, can just get to the encrypted database. And another thing is the key revocation. Key revocation will be like the scenario. For example, you have the USB token for HSBC or Barclays, and suddenly your USB card just suddenly gets stolen, and maybe in the train or someplace, and then you need to go to the bank and report it and get a new revoked for the revocation for the key. And to handle this type of revocation, they usually have some kind of methods and approaches. And of course, the most simple and naive one that is we go to the key distributed center or the trusted authority who generates the key, and then you ask him to distribute a new key. And of course, there's some other case. For example, the first case will be like the trusted authority will have a revocation list for the users, and then this type of revocation list, for example, Alice will put in the revocation list, and then Alice the next time window or time period will not grant corresponding secret key. And then in this scenario, the secret key will be tagged with the state. For example, state from T1 all the way to T2, and if you revoke in T2, and then it means that Alice will not get a secret key related to the update state T2. So Alice will not be able to decrypt all the ciphertext related to T2. So some researchers call this indirect approach, because it's not kind of very directly related to the revocation list. Another thing is about the revocation list. And the revocation list in these matters, we're going to grant the encryptor a power of revocability. It means that any encryptor can just put a revocation list into the ciphertext before the encryption, and then after that you just upload the ciphertext to the cloud-based store system. And if you are revoked user, you can download it, but you cannot decrypt it, because we can regard the revoked list as a kind of attribute set. If you're not within it, you cannot decrypt it, even though your some kind of maybe your identity is still there, and then your attributes keys already obtained, but it is for the past time period, so that you cannot decrypt it. And the last but not least, the solution could be the cloud assistant. The cloud assistant could be generally regarded as secret sharing. And this secret sharing parts will be like, I split the secret key into two parts. One part holding by the user, another part holding by the cloud. And then by doing the decryption, the cloud will do the first part, or the user will do the first part. And after that, the partial decrypted ciphertext will be decrypted by the other party, either the user or the cloud. But in this case, we need to fully trust the cloud. And our approach here is quite simple, the idea. We just combine the three things together. The first thing that is we use the revocation list. We grant the encryptor to has the power to encrypt the ciphertext, who can decrypt it, who cannot decrypt it. It means that we need to trust the encryptor. And then and by using the revocation list, because the revocation list can be controlled by the encryptor can always control the size of the revocation list. For example, I know that Anderson block will be expired, by tomorrow. So today there are still valid users. And then by tomorrow I can do a ciphertext Anderson block, but after tomorrow, Anderson blocks when they are expired, there's no need for put them into the revocation list. So in this case, there's no need to embed the elements of the revocation list into the ciphertext, which to some degree reduce the size of the ciphertext. And we also use the key update process. The key update process, we tag to the time period. So that's why this is time-based. And I'll explain a little bit further how to embed this time-space technique into the ciphertext later. And we don't need the cloud assistance. Instead, we deliver no traffic to the cloud. And of course, our scheme can be extended to support the ciphertext updates as well. And then the last thing, the technique we use is we use HIPE, hierarchical identity-based encryption, to shorten the size of the secret key. And then when we're trying to use hierarchy, and we embed hierarchy with the time. For example, the road is just a road. Sorry. And then some nodes down to the second level could be the year, and then the lower level could be months, and the lower level could be days. And then this is the feature comparison of our scheme with some existing works. And for the instant revoke, it means that there's no need to wait. For example, the key updated, we need to wait to some constant time slot so that the key update can be done. And the instant revoke, we let the encryptor to do the revocation. And then the no frequent key updates, and then cloud free. And then we also have a short revocation list which can be controlled by the encryptor. And the ciphertext update could be optional. So there's some definition for the time period. In our construction, we define our time period into the following formats. It should be the date and month and year. And then date, month, and year, this kind of corresponding values will be extracted as a kind of separate vector. And then this vector will correspond to each node values in the followings. So by talking about the construction, I would love to introduce the definition of the revocable ABE. And like the others revocable ABE, we need to use the revoke user list. We also embed with the time slot as well because it's time-based. And then the setup is relatively easy. And then the key gen, we need to embed the ID with it because we want to use some key updates. The key updates related to the ID. And then of course the attribute sets as well. And then the time slot. And then the encryption, we used this part we call it the decryptable time period. The decryptable time period is like the following example. For example, you have the key corresponding to only today. But if the encryption is for the, say, after the days till the end of this month, so you cannot decrypt it. But if the encryption is based on today, but your decryptable time slot is in this July, then you can decrypt the ciphertext. And the decryption is corresponding to use the secret key of your ID and the attribute set, which that attribute set has to match the LGP structure, which you define in the encryption. So that the user can decrypt and recover the plaintext. The security model, and we only consider that the selective adversary, which means that you have to put the revoke user list and the time slot, and then the target LGP structure before you play the game. And then we only can also consider the CPA scenario. It means that the adversary can only ask the secret key, and then after that we will just trying to do the send the challenge ciphertext to the adversary. And of course, the adversary with some constraints here. The first thing, In general, the constraint should be like, we cannot let the adversary to very easily to or straightforward and trivially to win the games, and that's it. So in this case, if the adversary can trivially win the games, these three conditions. First, the attribute sets satisfy the access structure, and the other thing it is the ID is within the revoker list, and the last thing that is the decryptable time slot is exactly covered by the previous query, secret key query. So our construction is secret key construction is based on this kind of tree structure. So as you can see that we have to build up a tree, but the rows here, that is extra component. We have to spend this extra cost into the secret key and the ciphertext. And then the second level you can see is the year, and the following levels are the months and the days. So for the construction, and because our construction is inspired by the Waters construction, and then as you can see, we try to embed the revocable users, the components into the capital F, and the R here is the maximum number of the revoked users. And then this is the extra part we need to put into the public key. And then this we want all the ways to VT. T is the depth of of the tree of the time slot. So in here, the tree view parts, the technical details could be referred to the paper, but I will introduce the tree view part here. And the tree view part is in this part, the D0 and D1 tiled and LJ tiled. As you can see that they're related to tau, it means that these three components are controlled by the time slot. So they need to be cancelled out because we treat the time slot like, for example, there's a lot of attribute sets. That this attribute set has a lot of components, and all of them are related to the time. So if one of the components is within this, it means that in here one of the components is within the set of the time period. It means that it matches because this time slot falls into the time slot it matches, so that it can decrypt this part. And the FI part is we use it to match the ID. Additionally, to match the ID components, you can see more clear in the encryption part. So in the encryption, we need to find coefficients first to satisfy this equation. If this equation is simple, it means that if the ID is in the revoked list, this FR of exact will turn to be 0. So if it is turned to be 0, some part of the decryption cannot be cancelled out. So this is our idea for the revocation. But of course, you need to find the Y1 all the way to YR plus 1. And then in here, you can see that this part, it is exactly the F. We just put into the F1 is in here. We just put all the component for the revoked users here for cancel out. And this part is for the time. And this is the original components for the attribute sets. For the decryption, first of all, we need to recover the capital F. As I mentioned previously, the capital F is kind of like these constructions. If the ID is within the revocation list, it will turn to be zeroed. So if it is turned to be zeroed and this part is invalid, so that we cannot recover the alpha 1, this other component with alpha 1 S and U. And if we go back to a little bit here, so this part is alpha 1U and this part is alpha 0T. So at the end, we're trying to recover these two parts so that we can cancel out the time and the ID at the same time. So if the ID is not equal to the ID1 all the ways to ID something within the revocation list, and we can recover these components. And another this part, we use the original attribute sets match the SS structure. And then the last this part, it means that your time period components within the time periods set which is defined within the ciphertext. So then you can recover another part. So I'll show you here. And the correctness is also shown in the paper. So in here, we can see that we have alpha 1, and then we have alpha 0, and then we can just cancel out these two parts. And the VJ part, we can, for the decryptable time periods, we can cancel out in this part, so we can recover the M at the end. So here is the efficiency comparison. I want to highlight two things. The one thing that is compared to the paper 29 and 26, our ciphertext size is not related to the N, which N is the maximum number of the user within the system. And another thing that is the decryption time is not also related to the users. And the secret key size, we need to relate it to the Z is the size of the HID trees we want to embed into the secret key, and then R is the size of the revocation list. And the security proof, we put the security proof into our full version, which can be found in the ePrint, and then, but our proof is not in a very simple and in a normal complex assumption. It's based on decisional queued BDHE. And then the tricky part here is about how to construct the secret key and how to embed the time, the crypto time period and ID into the ciphertext as well. So that's it. Thank you.
Thank you. Questions? Thank you. Thanks the speaker again.